my name is Moritz. I'm a developer relations engineer at Affinity, and today I'm going to give a workshop on generating on-chain metadata and assets for Ethereum NFTs. And before we start with that, I have to go over some theoretical stuff first, so we make sure that we actually understand everything that we are going to build. So I'm going to give you a quick intro to the internet computer. Then we are going to talk about Canister smart contracts, their unique capabilities, and how we can use those capabilities to interact with Ethereum smart contracts. Okay. Throughout the slides, there are going to be a couple of QR codes that you can scan for further reading material, but you don't have to keep your phone out all the time. You could actually just scan this QR code once. That will lead you to the slides. I think the display should be my slides, right? Okay, perfect. You can just scan this QR code once to get to the slides, and then within the slides, you can just click on the QR code, and it will get you to the respective further reading material. So by now, a couple of you probably already have their first question, and that is, what is the internet computer, right? This is an Ethereum conference. What is the internet computer? So in one sentence, the internet computer is a decentralized and permissionless cloud built on blockchain technology. And before we start with the presentation, I quickly want to get a feeling of the room. So how many of you have heard of the internet computer before? Okay, awesome. And how many of you have built on the internet computer before? Okay, and how many of you are planning on building on the internet computer? Okay, yeah, maybe we can increase those numbers at the end of this workshop. Let's see. All right, so a permissionless cloud built on blockchain technology. Let's add a bit more context to that. So after Bitcoin, and there should be my slides. At least I'm seeing one on my screen. Also ich sehe hier eine Slide, aber da ist ja weiß, oder? Ja. Okay, weird. Glitch. Okay, sorry. Weiß nicht, was das gerade war. Okay, genau. Nach Bitcoin and Ethereum is the internet computer is a third-generation blockchain, and it solves problems that Ethereum has not solved with its evolutionary step. And that means that the internet computer is a high-performant, horizontally scalable blockchain that is able to run very general smart contracts and even host web pages. And I want to underline the statement a little bit by quickly comparing some of the key metrics between the internet computer and Ethereum. Let's start with the transactions per second here. I see is 2 orders of magnitude more performant, same for transaction finality. Transaction costs even more, and for the storage costs, again, even more, with it only costing $5 to store a gigabyte of data for a year. And while the internet computer excels in those metrics, of course, Ethereum is constantly improving through solutions like sharding and layer 2s. And another thing that is not on this table is that the Ethereum community is, of course, and the ecosystem is, of course, way bigger than that of the internet computer, and that Ethereum is a proven and trusted technology that has been around and used for many, many years now. And for the use case of today's workshop, we are going to combine the high-performance capabilities of the internet computer with the security and decentralization that Ethereum is known for. So, with that out of the way, let's next talk about Canister smart contracts. So canisters combine code and state in one place. And when you want to deploy a canister, you first have to compile that canister from a high-level programming language, like Rust, for example, into a WASM module. And WebAssembly, or WASM, is a low-level and portable binary instruction format. And in theory, all languages that compile to WASM or that have an interpreter that can be compiled to WASM can be used to write canister smart contracts, and that includes Rust, which is what we are going to use today, or Go, C, C++, Motoko, JavaScript, Python, so many languages to choose from. Okay, so canisters are an evolution of smart contracts as you probably know them or think about them. And for us today, it's easier to think about them as decentralized server. So let's go over some of the unique features that canisters can offer that make them more similar to servers than traditional smart contracts. The first one here are timers. So canisters can automatically execute smart contract logic, either after a specified delay or periodically, so you don't need any off-chain infrastructure to do that. Then we also have the reverse gas model, which allows your users not to know anything about crypto, wallets, or tokens. And that works by pre-charging the canister with gas, and then the canister itself pays for the invoke computation. Canisters can also call into Web2 services, like, for example, an exchange rate API or an RPC node provider, or RPC provider for Ethereum. This is something that we are going to do later today. And yeah, this feature is called HTTP outcalls. And because canisters operate at web speed, users don't have to wait long for transactions to be finalized, and that offers them almost the same experience that they are used to from interacting with traditional Web2 services. The Internet computer also provides a secure and verifiable way to generate random numbers directly within smart contracts or canisters. And also, thanks to chain key signatures, canisters have control over a unique ECDSA key pair, and they are able to request signatures with the corresponding private key to be computed. And this enables canisters to natively hold, for example, Ethereum or Bitcoin or any other chain that supports ECDSA signatures, or tokens from chains that support ECDSA signatures. And we are planning on adding support for other signature schemes as well. Currently, we're working on threshold Schnorr signatures, and the plan is to release them by the end of the year. We talked about storage previously, but I didn't tell you how much you can store in a canister. So currently, you can store 400 gigabytes of data with plans to enable terabytes in the future. And last but not least, canisters can serve websites and answer API requests over HTTP. And this makes it extremely easy for developers and applications to integrate with your canisters. And it also allows you to deploy your entire dApps infrastructure on-chain, so also the front end. So now that we know about the unique features, let's talk about how canisters can leverage those to interact with Ethereum. And with the HTTP outcall feature that I mentioned earlier, canisters can actually read state from Ethereum. And they do that by making an HTTP outcall to an RPC provider with their request. For example, they want to get the logs for an event. And the result is then becoming available in the context of the smart contract after the response is getting back. But they cannot only read Ethereum state, they can also write it. And that works by leveraging the chain key signatures that I mentioned earlier. So in this case, we're using a threshold ECDSA signature scheme. The canister creates a transaction, for example, using ethers, RS, or Alloy in Rust, and it then asks the threshold ECDSA scheme to create a signature on the transaction. And the signed transaction is then being sent to an RPC provider, again, using the HTTP outcalls feature. And for this, canisters on the IC can trustlessly interact with Ethereum. Okay, and because building a canister that securely and correctly interacts with Ethereum can be quite challenging, we actually provide the so-called EVM RPC canister for that. And this canister acts as a gateway to Ethereum and other EVM chains. It's basically a helper canister that does a lot of the heavy lifting for us, and it allows the developer to focus on the actual use case without having to replicate all the necessary logic to interact with Ethereum. And some of the things that Canister does is that it, for example, calls multiple RPC providers instead of only one. And it then checks that the responses coming back from the RPC providers are actually consistent. And this removes the risk of centralization if you only call a single RPC provider. And it also provides convenience methods that we can use without having to assemble the JSON payload first. And it also provides the responses coming back from the RPC provider encoded and candid, which is our interface description language. And that means that the response is immediately useful in the context of a canister without first having to deserialize it into something that we can use in the canister. So now that we have the theoretical knowledge we need, let's talk about what we want to build. And the project we are building today boils down to building a co-processor for Ethereum. So as you know, Ethereum smart contracts are pretty constrained computing environments, and co-processors enable to extend the capabilities of Ethereum by offloading specific tasks to a more powerful environment. And in that case, that more powerful environment is the internet computer. A co-processor could, for example, calculate some complex enumerable function or run some crypto like AES or RSA, or in our use case today, generate and store NFT assets and metadata. Let's go over a example flow. So it starts by the Ethereum smart contract signaling that it wants some co-processing to be done by emitting an event with the details about the job. The ICP co-processor canister then regularly fetches logs from the contract using the EVM RPC provider, the EVM RPC canister and timers. And upon seeing a new job event, the canister runs the requested job. And during the processing, the canister can do many things. It could, for example, store data or make transactions to other chains, call other canisters, and so on and so on. So basically, a lot of freedom here. And if needed, the result can be written back to the Ethereum smart contract as well. And here again, we are going to create a contract call in the canister, sign it with threshold ECDSA, and then send it to the network through the EVM RPC canister. And in this callback function, we assert that the caller is actually the co-processing canister to make sure that no one else is able to submit results that shouldn't be there. And because this co-processor architecture is very versatile and can be leveraged for a lot of different use cases, we actually provide a starter template for that, the so-called Chain Fusion starter. And here, of course, the co-processor logic is already implemented, and the developer only needs to worry about what computation they want to carry out in a job. And this starter template under the hood also uses the EVM RPC canister to interact with Ethereum. And it comes with a dev container, which is basically a Docker image with all the dependencies pre-installed for minimal friction to start building right away. And this starter template is also what we are going to use as a starting point for today's workshop. So finally, what are we going to do? We are going to generate and store the metadata and the assets for an ERC-721 contract fully on-chain using the Internet Computer as a co-processor. Why are we doing this? Because generating assets and metadata off-chain bears the risk of rigged mints and centralization. Generating them on-chain is not really practical due to the extremely high cost associated with it. And storing them on IPFS doesn't really allow for dynamic NFTs in a decentralized way. So what we want to do is we want to enable fair and fully decentralized autonomous mints, and we also want to enable fully on-chain dynamic NFTs. And how are we doing that? We are going to start from the Chain Fusion starter template to then, on top of that, build a co-processing canister that listens for mint events from an ERC-721 contract. And upon seeing such a mint event, that triggers the metadata and asset generation using the on-chain randomness provided by the IC. And this is the last slide. This is a sequence diagram to visualize the entire flow. I think this is very small, actually. But on the left-hand side, there is an ERC-721 contract deployed on Ethereum. On the right-hand side, we see the EVM RPC canister and the Chain Fusion starter canister deployed on the Internet Computer. And the sequence begins with the user minting an NFT on the ERC-721 contract, which emits a transfer or mint event. And as we already know by now, the Chain Fusion or co-processor in general regularly fetches the logs from the ERC-721 contract via the EVM RPC canister and using timers. And then the Chain Fusion starter executes a so-called job for each mint event it sees. And in this case, the job is that we generate and store the assets and the metadata for the NFT using on-chain randomness provided by the Internet Computer. And because canisters can serve web, the assets, so both the metadata and the actual image, are available via HTTP after the generation immediately. And if we want to get to the URL that serves the metadata, we simply follow the URL returned by the token URI method on the ERC-721 contract. Okay, there should be QR codes here. Okay, now they're here. Yeah, so if you want to code along, scan the first QR code, which is the link to the starter repository that we are going to use. And because time is limited, I don't know if you are able to code along with me. Maybe it's a bit too quick. So on the bottom QR code is the outcome of today's workshop. So if you are behind or something, you can just copy-paste code over, and maybe that way try and catch up. Okay, so let's head over to the repository. And the first thing we are going to do is that we are going to create a new repository off of that template. And I'm just going to call this workshop. And as soon as that one has been created, we are going to start one of those dev containers, or how GitHub calls them, code spaces. And we're actually going to click on those 3 dots here, and then we say new with options because we want a more beefy spec than the spec that it usually runs with. And I'm going to go for the 8-core, 32 gigabytes of RAM here. And I would suggest you to do the same. And while we are waiting for this to run, so this opens VS Code in your browser, but for some reason it doesn't really work for me, so I'm just going to connect with my local VS Code installation. You can do whatever you want, either use the one in the browser or your local installation. While that container spins up, we are quickly going to go through the existing infrastructure. So first there's this coprocessor smart contract that we basically went through in Ethereum. And as you can see, it has a function here called new job that is payable. So if you pay 0.0 Ether to it, it emits this new job event and it transfers the 0.0 Ether to the coprocessor contract canister so that that one can, first of all, pay for the computation and also pay for writing the result back to the smart contract. And to write back, we are going to use this callback function down here, and that checks that the sender of the message is the coprocessor to avoid anyone else writing results. And then we go into this Chain Fusion backend here, and in here we have our job module, and that contains the logic that is being run on each new job event that we are seeing. And this one is pretty simple. We basically just calculate the 20th Fibonacci number in this line, and then we are going to write that result back to the Ethereum contract, and that's it. And what we are going to do in this workshop is that we are going to replace the coprocessor contract with an ERC721 contract, and we are going to replace the job logic here with a logic that generates the metadata and the assets on-chain using the randomness provided by the IC. And what we are not going to do is we're not going to write anything back to Ethereum, so just this coprocessing as kind of like a side effect. Okay, so by now I think this should have spun up, so I'm going to click on the 3 dots again and then click on this Open Visual Studio Code, which will connect my local VS Code installation to this dev container. And the first thing we are going to do here is that we are going to replace the coprocessor smart contract with an Ethereum smart contract. And to get this Ethereum smart contract, you can go to book.getfoundry.sh, and then you go into chapter or section 24. And Foundry is basically the smart contract development toolchain we are using for our ETH contracts in this workshop. So once you are there, you scroll down a little bit. It's not the first implementation. It's actually the one here down at the bottom that says extending our NFT contract functionality and testing. We're simply going to copy this and paste it back into the coprocessor. And we are also going to rename it to nft.sol. And now there's a bug because the base contract, the ownable base contract, actually expects a constructor argument. So let's add that real quick down here. So we write in line 25 ownable, and then this contract should initially be owned by the sender of the message, so basically the deployer. And the next thing we are going to do is that we are going to modify the script that we are using to deploy this coprocessor locally, and now we are going to, of course, deploy our NFT smart contract. So we're going to modify the import up here. We can get rid of this argument that we are not needing anymore. We're going to rename this to NFT, this one to NFT as well. And here we're creating a new NFT contract. And now we have to also change our constructor arguments, and the smart contract expects a name, a symbol, and a base URI. So the name is going to be DappCon, the symbol is going to be DC, and the base URI This is actually a method that you can call on the smart contract called token URI. And what it does is it concatenates the base URI with the token to kind of form like a URL. And that URL usually points to a JSON file, and the JSON file is basically the metadata for the NFT. And as I said, canisters can serve web. So in our case, we are going to use a canister URL as a base URI. And that canister URL follows a certain schema, so it always starts with the canister ID, which is basically the contract address, followed by a domain name. And the domain name, because we run this locally, is localhost. And then we also have to specify the port that our local internet computer node runs on. So you can find the contract address or the canister ID if you go to dfx.json in the root folder. And then here it's the first canister basically defined, Chain Fusion backend, and this is the ID. So we're going to use HTTP canister ID .localhost and then colon 4943 4943 and then a slash. And that's basically it. Now we also want to mint a couple of NFTs when we deploy this. So we are going to rename this to NFT and then mint2, which is an argument that is exposed on the smart contract that expects an address to mint a token to. I'm just going to copy a random address from Etherscan to do that. So let's mint it to this address. And the value that we have to send along is 0.08 Ether, because this is the mint price that the contract specifies. Okay, now we have the Ethereum smart contract implemented. Let's continue with the coprocessor. So for this, we go into source, Chain Fusion backend, again source, and then into the job module. And in here, we're going to get rid of the logic that currently exists, and we are also going to rename this new job event to mint event. And now we can get rid of this debug because we don't really need it. And yeah, the mint event is actually a transfer event, but we only listen for transfers from the 0 address. Thus, we are going to just call them mint events. And you can see the event structure if you go to the definition or the specification of ERC 721 and you search for transfer, you will find this entry here. So it has basically 3 attributes: a from address, a to address, and then also the token ID. And in our use case, we only care about the token ID. So let's rename this to token ID. And now we have to modify this from method or function down here as well, because initially all the events that received by the canister are basically just, by the EVM RPC canister, are basically just generic logs, and we now have to convert the generic log entry to a mint event. And to do so, we need a token ID. And to get access to this token ID, we look at the topics field that each log entry has. So this is a vector of strings that you can see in the struct. And the first item of this topics field, so of that vector, is always the event signature. And that is a Ketchak 256 hash of the event name and the input argument types. And the rest of the items are indexed arguments of the event in order of their appearance. So all of the arguments here are indexed. So the item at index 1 would be from, index 2 would be to, and index 3 would be token ID. And that's why we are going to take the third, or the item at index number 3. And then, of course, we also have to rename this one to token ID and this one to token ID as well. Okay. This one is actually also a mint event. Okay, so the next thing is that we are going to get random bytes from the internet computer, and for that we are defining a variable called random bytes, and that calls, or that is being filled by this method called random bytes that is asynchronous, so we await it, and that's basically it. Now we have to implement random bytes. And random bytes gets random bytes from the system basically, and it returns a 32 byte array. So an async function called get random bytes, takes no arguments, and returns a 32-byte array. And in here, this is a tuple what's being returned, so we destructure it, and we make a call to raw rand, which is an asynchronous method, so we await it, and it could fail, so we expect should not fail. And now we have to import this raw rand, and we import it from the IC CDK, which is basically a canister development kit, and this is the path I think VS Code takes that away from you if you're using VS Code, which we probably all do now. Okay, and now we have to convert this byte vector into a byte array. So we call raw rand and then try into, and then because this could fail again, we expect should not fail. This is of course not how you should do it, but yeah, for the sake of time. All right. So next we are going to seed a random number generator using those random bytes. And for this we are going to use char20 from seed, and the seed are the random bytes that we just obtained from the system. Okay, so now we have a random number generator seeded by the randomness provided by the system. And next, we are actually going to generate the first, or the attributes for our NFTs. So let attributes, new variable, and we are going to call a function called generate attributes, and that takes a reference, mutable reference to the random number generator. So let's implement that method. First, we are going to add a new struct, the attributes struct, and that has two fields, a public background color, which is a string, and also a public circle color. So you maybe already have a little bit of an idea what this NFT is going to look like, which is also a string. Okay, now generate attributes. Oops. This takes a mutable reference to a random number generator, which is char20, and it returns the attributes struct. So we are just going to create this attributes literal in here, and we are going to say the background color is going to be the value of a function called to select value that takes a random number generator, and the same for the circle color, which is again a call to select value where we pass the random number generator. And now, of course, we have to implement select value. So let's implement that one. And this one takes, again, a mutable reference to the random number generator. And it returns a string, actually. So first we are going to, because our NFT is actually going to be in SVG, I didn't mention it yet, first we're going to define a couple of SVG color keywords. So we have an array here which contains a couple of keywords, color keywords, so we maybe have blue, red, and yellow, and green. And then we associate weights with those color keywords. So the higher the weight, the higher the probability that this specific color keyword is going to define either the background or the circle color for the respective NFT. And they are all going to have a weight of 3, except for green, which is going to have a weight of 1. So green is rarer than blue, red, and yellow. And now we are going to create a weighted index distribution. Oh, sorry, yeah, of course. Is that good? Or more? Yeah? Okay, sorry. I hope you could follow along still, kind of. Okay, weighted index. let's import this, and we are going to create a new one based off the weights that we specified, and we're going to unwrap this. And now we're going to actually select our color keyword by picking a random value from the array using the weighted index distribution and the random number generator. And because this is not a string yet, we have to convert this to a string. And now what's missing is that this sample here expects that you import this distribution from the rand crate. So we are doing that as well. Okay, now we have the attributes for our NFT. So we have a background color and a circle color. And the next step is that we want to generate and store the metadata for the NFT. This doesn't return anything, it just has a side effect. Generate and store metadata. And this takes a pointer to the mint event, or a reference to the mint event, and also a reference to the attributes. So let's implement this down here as well. Generate and store metadata. It takes a reference to a mint event and a reference to the attributes, and it returns nothing. So in here, we are going to create the JSON metadata using a library called SerDJSON. And then we are going to serialize that JSON into a byte vector variable that we call body. And to write JSON literals in our Rust code, we are going to use the JSON macro. So let's define the metadata variable here. Let's use the JSON macro. And let's write the metadata basically. So the first one is the name. The name is going to be a formatted string that consists of DappCon number, and in here in the parentheses we're going to insert the mint event and then the token ID. This is a typo, attributes, and this I have to import as well. Then we are going to also point to the actual image, which is the actual SVG that we are going to generate in the next step. And here again, we use the canister URLs, right? So we are starting with HTTP. Then this is going to be our canister ID, then localhost, and then 4943, which is the port that the local internet computer node runs on, and then this is the token ID, and the file type or the file ending is SVG. And now we have to fill in the curly braces here, and we are doing that by filling the first one in with the actual canister ID, and I don't have to copy paste it because the ICCDK provides a method for me to get the ID of the contract that I'm executing this function in. And because this is not a text, I have to convert it into a text. And the other thing is, again, the token ID associated with the mint. All right, and now we're going to generate the attributes. So if you would trade or sell this token on OpenSea, you would have a nice representation of the attributes associated with the NFT, which is the background color and the circle color. And this is an array of objects that contain two keys or fields. The trade type, which for the first attribute is the background color, and then of course also the value associated with the trade type, which we are going to get from our attributes. And of course this is going to be the background color, and now I have to clone this as well. And now for the second one, I'm just going to copy paste this, and I'm going to rename the background color, of course, to circle color. And then down here again, I'm going to use circle color. So this is it. This is the metadata for our NFT that points to the actual image that is stored on the canister as well, served via HTTP. All right, so I said we generate the metadata, but we also need to serialize it into a byte vector. And that's what we are going to do now. So we're going to create a new variable called body. And here we're going to use the toVec method that is exposed by 30JSON. We are going to pass a reference to the metadata in this. And then we are going to, because this can fail, expect that this should work. Of course, again, not best practice. All right. So to store our asset, to now later on surface it to the web, we use a method that is already provided with the starter template. And to be able to import this method into our job module, we have to first go back or go into the library module. And in here, all the way at the top, in line number 9, there's this mod storage that is currently commented out. So we are going to uncomment that. And now we have access to a method that is called store asset. And that accepts 2 arguments. The first one is the actual path that we want to serve the asset from. So let's define that one first. Because it's a metadata, it traditionally, for some reason, doesn't have a JSON file ending. It's just a token ID, and that's it. So yeah, in here, we are again going to format. And this is going to be simple because it's basically just going to be the token ID, and that's it. And in here, again, we use the mint event and the token ID. And for the actual asset, there's a struct that we are going to import that is coming from the storage module or crate. So let's import that. And now, basically write out the literal. This struct has 2 fields. The first one are the headers that we want to associate with the asset that we are going to serve. In here, we are only going to set the content type, which we're going to set to a text/JSON. And then also the body of the asset, which is the byte vector that we serialized in a step before. So let's start with the headers. And here we're going to use a vector. A header is always a tuple of 2 strings, the name of the header, which is content type, and then the actual value, which is text/JSON. And of course, both of these have to be strings. Okay, now we have the header. And the next step is to just use the body down here. And that's it. Now we generated and stored the metadata of the NFT, and we also made it available through HTTP. And the next step is that we are going to generate and store the actual image. And again, we are going to pass the mint event and the actual attributes to this method. Oh, that's wrong. Mint event and attributes. And in here, as I hinted and as the name also suggests, we are going to generate the actual SVG. And for this, we are going to make use of a crate called SVG to create the SVG, and then we're going to serialize that SVG into a byte vector again. So let's start with the background. We're going to use a rectangle node. I have to import this first from the SVG crate. So a new rectangle node, then we're going to set the width of that node to 100%. And we are also going to set the height of this to 100%. And we're going to fill it with the attribute that we generated for the background. So attributes and then background color. And again, we have to clone this. So that's all we need for the background. And now we're going to create the circle node as well. And again, we are going to import this node from the SVG crate. We're going to create a new one. We're going to set the center of the circle on the x-axis to 50, and the same thing for the y-axis. And then we're also going to set the radius of this to 48. And now, of course, we also have to fill this with the color. And in this case, this is, of course, not the background color, but the circle color. And now we have our background. On top of that, we have the circle. Now we can create the actual SVG document. And we are going to use the document exposed by SVG. And we are going to set, I have to import this first. We are going to set the view box of this to 0, 0, 100, and 100. So this is basically a 100 times 100 pixel or dimension SVG. And now we're going to add the background to this, the background node, and then we are going to add the circle node. And for storing the actual asset, we are going to just copy and paste the store asset function from generate and store metadata and paste it up here. And the only thing we have to do is that we have to change the path. So this is not just a token ID, but it's the token ID.svg. And of course, before that, we have to serialize this into a body. So document, and then we do toString, and then into bytes. That should be sufficient. And the content type is, of course, not a text or JSON anymore. It's now an image, and in this case, a SVG. Yeah, now you generated your metadata, you generated your image, both using a random number generator that in the first place generated the attributes for the NFT. So that's basically all we wanted to do in our job. Now, I said a couple of times that canisters can expose data via HTTP, and to enable that, canisters have to expose a method, basically an entry point to the canister that is called HTTP request, and expects the system expects that this method takes an argument of type HTTP request and returns a HTTP response. So to enable our canister with this functionality, we are going into the lib.rs module, and we scroll all the way down, and then we uncomment this method that you find here, and we also have to import some of the missing types and the missing getAssets function from the storage trait, which is basically retrieving the assets that we just previously stored, so the metadata and the actual SVG. And that's basically it with regards to the backend, with regards to building this coprocessor canister and building this ERC 721 contract. So the only thing left to do now is that we have to modify our deploy script, which basically deploys all of this locally and lets us see the result of what we just coded. So in here, so we use Anvil for our basically Ethereum network locally. That comes with Foundry and an RPC node built in. This is where we start Anvil. We need this caddy server, which is basically an HTTPS proxy, because otherwise the HTTP outcalls don't really work, so you don't really need to know about it, but that's just there for that reason. So after caddy start, we are going to insert the script that actually deploys the Ethereum smart contract, and we can go all the way down to the deploy script, and we can copy the last line and go back up and insert it after caddy start. And here we have to make a couple of changes. The first one is that the script is called nft.s.sol. We can keep this entry point. The fork URL is the same. We also want to broadcast all of the transactions, but we can remove this part after broadcast. So this now deploys our NFT contract locally and basically just runs the script that we defined here to also mint a number of NFTs so that we can emit events that we can then later on see using the coprocessor canister. And another thing we have to do is that we have to modify the topics that we want to listen for. And we can do this down here where we deploy our coprocessor canister or this chain fusion backend canister. And previously we were listening for new job events, right, in the initial use case, but now we want to listen to or for transfer events. And as I mentioned, the first element of this topic is always the event signature, so a catcher cache of the event name and the input argument types. So if we go back to the ERC-721 contract standard, we can check this transfer event here, and we see that it consists of 3 attributes, again an address, and a uint 256. So all we have to do now is we look for a online tool to create a catchuck 256 hash, and we're going to pass in the name of the event and then the attribute types, which is address, and then uint 256. And we close the parentheses. And that's it. This is the event signature that we are going to pass. And now we listen for transfer events. Another thing we have to do is we have to add this 0x in front of this. But we don't want to listen to transfer events, right? We want to listen to mint events. So the second element of this topics that you can also, of the logs topics that you can also filter for is going to be this. Where is it? This from address, right? So, and we are specifying the 0 address as the from address, and that means that we are only seeing transfers from the 0 address, which are basically mints in most of the cases. So I'm just going to add a bunch of zeros here and copy paste them until we have the same amount. It looks good. And now we can get rid of this old code down here, so basically everything after sleep, or with everything after line 66 can be removed. And now we have our deploy script, and hopefully I didn't do any mistakes. Let me go back and scan over this real quick. So yeah, of course you can get rid of the imports that are not needed anymore to make everything nice and clean. So there's one thing, yeah, this one is not needed anymore. You could also delete this entire folder up here because it contains logic that we don't need anymore. And now let's try running the deploy script. So initially, like I said, we spin up this local Ethereum network. We then deploy our Ethereum smart contract, the ERC-721 contract. Then we are going to mint 10 NFTs. And once all of those transactions are successful, we are then going to deploy the EVM RPC canister, which is basically this gateway canister. And this is happening here. And this boots up then, loading a bunch of stuff. Those are just like logs, right? If you deploy in mainnet, you wouldn't see that. And last but not least, we're going to deploy the Chain Fusion backend. And then the Chain Fusion backend, as you might remember, starts to fetch logs from the ERC-721 contract that we deployed locally, and it fetches logs or events that are mint events. So there should be 10 of them that we should see. Okay, so there's calculate result. I think I just deleted that. So let's just rebuild. So while this is deploying, I can already talk a bit about what's going on next. So next we're going to use cast, which is also coming with Foundry, and that allows us to make calls to the smart contract that we deployed locally. So we're going to use cast call, then we are specifying what RPC we want to call. So dash dash RPC dash URL, and this equals to 127.0.0.1, and then the port that Anvil runs on is 8545, and then we have to specify the contract address that we want to call. So we can get that from the deploy script again. So it's this one here, because the deployment process already starts from the beginning. The contract address is deterministic, so I can just add it here and it doesn't change. And then we also have to specify what we want to call on this contract. And that is the, as I mentioned earlier, the token URI method. And that takes one argument, which is a uint256, and it returns a string. And now we also have to specify the token ID that we want to get the token URI for. Let's see. Submit result. Yeah, I should delete this and this one as well, of course. Weird that I didn't get any red squiggly lines, but as always, the compiler, luckily, is your friend. So yeah, this might take another minute. Sorry. But maybe I quickly summarize what we achieved. So again, we have this ERC-721 contract deployed locally, right? We mint 10 NFTs on it. Every mint emits an event. Then we also have this coprocessor canister deployed locally. This coprocessor canister listens for events on the ERC-721 contract. Every time it sees a mint event, it then generates, or first, let's go through the job actually. It first gets random bytes from the system. It uses the random bytes to see the random number generator. Then we use the random number generator to generate the attributes for the NFT. The attributes are the background color and the circle color. And then based on the attributes, we are generating and storing the metadata. We are generating and storing the image. And we are exposing both via HTTP. And if the demo gods are with me, this should run now. OK, yeah. So now our canister, the Chain Fusion backend canister, found logs to process. And for each log, which is basically a mint event, it's now running the logic that we defined in this job method here. So now I should be able to call the token URI method on the ERC-721 contract. If we remember, we passed in the canister URL as a base URI. This gets concatenated with the token ID. So we receive basically a URL back from this call. Let's try this. And this is this canister URL that should hopefully now point to the JSON that we generated. And luckily, it works. So as you can see, we have the attributes in here, the background color, the circle color, in this case, blue and red. We have a link to the image, which is again a canister URL, so this is also stored on the canister. And we have the name, which is DappCon #1, because this is the first NFT that we minted. And if we now, for the sake of demonstration, let me just copy this, follow the actual image URL, you can see that this is the token or the NFT that we created. So the background color is blue as expected, circle color is red, so everything worked out. So one thing I didn't have the time to implement is this dynamic NFT claim that I made, right? I said that if you store them on IPFS, they are not really dynamic in a decentralized way. But if you think about the architecture that we built already, and we would imagine that on this ERC-721 contract, we expose another method that we maybe call reroll for the sake of the demonstration. And that method, if the owner, you pass in the token ID, and you have to be the owner of the token ID to call the method. And if you do that, that method emits maybe a reroll event. And then we can deploy our Chain Fusion canister in a way that it doesn't only listen for mint events, but it also listens for reroll events. And then in the job here, when we parse or convert the log entry into a mint event, we could also add like a a second case where it's a reroll event. And then depending on whether it's a mint event or a reroll event, you could have some custom logic in here. You could, for example, in the simplest case, in both cases, no matter if it's a mint event or a reroll event, you just execute the same logic. So you get random bytes again, you see the random number generator again, and you generate the attributes again. So basically, you give the user a reroll for their mint. And this is, fully decentralized. It's a dynamic NFT because not only the metadata changes, but also the asset change. There's no centralized infrastructure involved. Everything is running on two layer ones, basically the internet computer and Ethereum. And I know NFTs might not be as cool as they were a couple of years ago, but I think with this, there are a number of very nice use cases that open up. And because there are only 5 minutes left, let me quickly go back to the final slide here. So if you have questions, I'm around all day. So if there's anything that wasn't clear, I know this was a lot to take in, and I was pretty quick, and probably no one was able to follow along. But if you have any questions, you can ask me. And if you don't want to ask me, you can join the community Discord. So we have a Discord server with our developer community. You can also join our developer forum, where you can ask lengthy questions. And I'm pretty sure there are people either with inside Affinity or outside Affinity that are more than happy to answer your questions. We also have a pretty big developer grants program. So we're allocating $200 million or Swiss francs for developers that are building cool things in the ecosystem. I'm part of the grants committee, so if you have questions about that, feel free to ask me. Then if you're still wondering what is the internet computer, there's a nice video series that we did together with Encode Club that you can find in this link. And then we also have a wiki page that kind of like shows the similarities and differences between the internet computer and Ethereum from the perspective of an Ethereum developer. And I think I have time I have 3 minutes roughly, so if anyone has a question that I can answer quickly, I'm more than happy to take it. If not, I'll let everything sink in for you. Did anyone follow along out of curiosity, or try to follow along? Yeah, and it was probably too quick, right?
Without coding, it's fine.
Oh, okay. Okay, awesome.
Can you show the QR code of the finished thing again?
Yeah, sure. Sorry. It's here. There's also, this is basically the stripped down version that I try to fit into 45 minutes of live coding. So if you go to the Change Fusion starter repository and you scroll down, there's a more elaborate implementation of this all the way at the end. That's the same thing, but it does a couple of things differently, and it's like more realistic for a production environment, while this might lack. Probably you want to have more than 2 attributes.
Are there solutions to the developer experience? Because it took 1 minute to run the code again, which is not good to developer experience, I guess. Is it faster, or is there a solution for that? Sorry. So I was asking if there's a solution for the developer experience, because it took about 1 minute or something. Because it took about a minute or something to run the code, and this is quite a lot. So are there solutions to this problem?
Compiling the Rust code is inevitable, but because I compiled it the first time, or because this deploy script, because I compiled it the first time, it took longer. Usually, I think there's some caching going on, and not everything has to be recompiled. So if I would run this again, it wouldn't take that long, hopefully. But I think you always have to compile the Rust code into this WASM module. So that's probably something that can't be sped up or speed up. Sorry. Okay, then thank you everyone for attending. I appreciate your time, and like I said, if you have any questions, more than happy to answer them. Bye.